It's okay. It's okay. Good. That's good. I saw you had the urge to bark and you didn't do it. You gotta sit over there in the lecture. Okay, let's go ahead and get started. So, on Tuesday we had the snow day, yay. And, I recorded a lecture about trees, which you saw. And so today we're gonna pick up talking more about trees. And in particular, we're gonna be looking at, counting trees, and also we're going to be moving into counting the number of spanning trees inside of a graph, and that will lead to the matrix tree theorem, which is really cool. And we'll maybe get to this statement today, and then next class we'll have like the proof of the matrix tree theorem. So just as like a warm-up, I'm going to ask you how many trees there are. This is way too How many trees are there on the vertex set, the numbers 1 up to n? So not how many isomorphism classes, but how many, like actually how many trees are there? And I'm going to give you time to think about how many there should be for maybe like n equals 1, 2, and 3. And possibly you may get to 4 as well. So I'll give you time to think about that, and we'll discuss after, just as like a warm up. I'll also just say the answer for n equals 5. Okay, so what do we get? So for n equals 1, we only have there's only one tree, right? You just have the one vertex named 1. And then what about for 2? How many are there? So we have 2 vertices. 2. Why 2?
Because there's the one with no edges and then there's one with one edge.
Okay, so good. So a tree is supposed to be connected.
Okay.
Yeah, so this is just like refresher from the recorded lecture. Yeah, so a tree, so if the question was like how many forests, then you could have a disconnected one, right? But for a number of trees, we have to have just an edge here, and that's the only possibility. Does that make sense? Okay, what about for n equals 3? How many did you all come up with? 4? 1?
It's like three vertices.
Yeah, so we have 3. Yeah, but they're also labeled. They like the vertices have names.
So would there be 3, like, in for each different one, there's one that has degree 2?
Yeah, so basically all 3 of them are gonna look like this, and then it's just a matter of like ways of labeling these. And to pick a labeling, all we need to do is choose like who is the middle vertex. So there's one that looks like having 1 and then 2 and 3 on the outside, and then we could have 2 in the middle and 1 and 3 on the outside, and then 3 in the middle and 1 and 2 on the outside. Okay, good. And then I'll go ahead and tell you how it goes for n equals 4. So there's basically 2 isomorphism classes. One looks like this, and one is a path. And then there's, for the, you call this one the star. For the star, there's just 4 like 4 ways of labeling it, just depending upon how you want to label the center vertex. So there's 4 of these. And then for the path, there's 12 of them. And I think the easiest way to see this is like, let's pick the outer 2 vertices. So there's 4 choose 2, which is 6. ways to do that. And then for the inner vertices, all that matters is like what order they go in. So then there's two ways to pick the order of the inner vertices. Does that make sense? Okay, so in total here we get, let me write the totals actually. So we have 1, 1, 3, and then here we have 16. And then for 5, I'm not gonna draw out what they all look like, but there's 125 of them. And so as this goes on, the general pattern is that there are n to the n minus 2 many for starting from n equals 4. And this is called Cayley's formula. Oh no, it still works for n equals 3. So, and I guess for smaller. Okay, so I misspoke. So yeah, this is the formula. So, okay, so there's multiple proofs for this, and in this class we will actually see multiple proofs. I think probably the easiest one is as a corollary of the matrix tree theorem, which we'll see next class. So that's like the easiest version, but the proof is not so satisfying because okay, so what do combinatorialists like? They like counting things, but additionally, like more than saying like how many of this object are there, it's interesting to say, here's a bijection from the objects I want to count to a set that obviously has that size. Does that make sense? That's like kind of a stronger, like it gives you a correspondence between like these things and some set that obviously has the claim size. So today we're gonna give that proof for trees. And basically how this will go is that, so we're gonna give, it's like, what is our goal? Is to prove this by giving a bijection to a set of size n to the n minus 2. And you'll actually see pretty often that there will be an argument as to why. So this is like in general in combinatorics. Oftentimes you can prove like you can count some objects, but then it's an open problem to give like a so-called bijective proof, like to provide a bijection to like a good set. So this is like what we're gonna do today for trees. So the set that we're gonna give a bijection to is the following. So I'm gonna let S be, this is gonna be our vertex set, so it's gonna be the numbers 1 up to n. And then there are n to the n minus 2 ways to form a list of length n minus 2 with entries in S. So I'll just write that down. So there are n to the n minus 2 ways to form a list of length n minus 2 with entries in S. So let's just see why for a second. So if I want to make a list of length n minus 2, so I have n minus 2 entries. For each one, I have S, size of S many choices, so n choices for each one. So to decide how many there are in total, I would just multiply all of those possibilities, and that gets me n minus 2 many n's. So n to the n minus 2. So I'm going to denote this set of lists by s to the n minus 2. Okay, are there questions so far? So my goal now is going to be to give like a bijective correspondence between trees and lists. So I want a way to take a tree and encode it as a list, and then also a way to take that list and recover a tree. So we want to take trees on S and correspond those to elements of S to the n minus 2. And you call just like, what are these lists called? So we encode a tree by an element of S to the n minus 2. And this is called its proofer code, or a proofer sequence. Okay, so I'm going to give you two algorithms. So one will start with a tree and make its proofer code, and then the other way will start with a proofer code and make a tree. So I think that taking a tree and making a code is easier, so we'll start with that. So here's like an algorithm. And then we need to prove that that this actually is bijective. Okay, so for input, I'm going to have a tree on the vertex set S, and then my output is going to be its proofer code, which I'll call f of t, and I'm going to write the entries as a1 up to an minus 2, and this is an element of S to the n minus 2. Okay, so here's how it goes. At the ith step, I'm going to delete the smallest remaining leaf, like the one that has the lowest number or label. And then I'll let a sub I be the neighbor of that leaf. Okay, and that's it. So let's do an example. Yeah, and also just like as a reminder, because we didn't actually talk about this in person. So like leaves on trees are the vertices that have only one edge. So they have degree 1. And so there is just one option for what J sub I is, right? It's the only thing that's connected to that leaf. Okay, so let's do an example. So this is going to be my tree. And here's how the leaf labels are. Okay, so step one, we're gonna delete the least remaining leaf. So here's our leaves. Are these ones circled? So 2 is the smallest leaf. So I'm gonna delete that one, and then I'm gonna record what its neighbor was. Let me just, so the neighbor of 2 is 7, and I'm gonna erase 2. Does that make sense? Other questions about that step? Okay, so then step 2, the least remaining leaf is 3. So I'm gonna delete 3 and remember that its neighbor was 4. Okay, next step, least remaining leaf is 5 and its neighbor is 4. So I'll erase that. Okay, now the least remaining leaf is 4 and it's connected to 1. So I add a 1 to my sequence and delete 4. And now we have 6, which is connected to 7. And 7 is connected to 1. Okay, and now we stop. So I guess maybe in the algorithm, I'll add that we stop. There is. Okay, so that's our proofer code. Does that make sense? Yeah,
So these codes, unique to isomorphisms for graph. But the only way to get that code is with this from isomorphism, or exactly this.
it would be exactly this tree. Yeah. So if you switched up the labels, like you'd get a different code. Yeah. That was a good question. Yeah. So we'll prove that like every tree gives you a unique code, and then furthermore that every code corresponds to some tree. Yeah. Are there other questions? Would it help to give you guys time to do another example? Do you want to try another one? Okay, I'll give you, so just as an exercise, let's make another tree. Uh, okay, so go ahead and write the proofer code for this tree. Okay, did you all get this proof for code? 14411. Okay, looks good. So, now we have a much more difficult task, which is reversing this process. So I'm gonna tell you how to take a code and write a tree. And then we'll do an example. So, now we're gonna take take a code and make a tree. And the goal is basically just to reverse the process that we just did. So here's how it goes. So we're going to start with a set S of isolated vertices. And then what we're going to do at each step is we're going to create one edge, and we're also going to quote unquote mark a vertex. So at every step, there's going to be some set of like marked vertices that we're going to do something with. So, okay, so at each step, we'll add one vertex, or sorry, one edge, and mark one vertex as follows. So at the ith step, what I'm gonna do is I'm gonna let K be the least among the unmarked vertices. And we want this to be the least among the unmarked vertices that are not in A sub I up to A sub n minus 2. So there's like some set of candidate vertices that are like not in AI up to AN minus 2 and not one of the marked ones. So we'll take the least among those candidates. And then I'm going to add the edge K A sub I to the list of edges and mark K. So the marked ones are kind of like the ones that we've already dealt with in some sense. And then once you repeat this n minus 2 times, there's 2 unmarked vertices. Because at every step we're marking one vertex and we've done n minus 2 steps, so we'll have 2 unmarked vertices. And we're going to join them to make the final edge. Okay, so I think this is confusing until you've worked out an example. So let's do that. And I'm gonna just reproduce the first example and then maybe we can do the second one as well. So I'm gonna start with this code and reproduce the tree from before. And I'm gonna say that when I was preparing this lecture, I did not flash this exercise, and it actually took me 3 attempts to correctly reproduce the tree. So it's very easy to make errors in this, but it can be done. So, okay, how many vertices are we starting with? So we're going to start with a set of isolated vertices. How many should there be? Yeah, 8. Why 8?
Because that's more than multi-cap.
Yeah, so the length of the code is 6. So that means we need 8 vertices. So let me draw 8 vertices, 8 isolated vertices. Okay, so now the algorithm says, at every step, I'm going to let K be the least among the unmarked vertices. And this should say and. Okay, so we don't want K to be a marked vertex. There's no marked vertices so far. And we also don't want it to be in a sub I up to a n minus 2. In this case, I is 1. So it's not allowed to be any of these numbers. And we just want to pick the least among the ones that are not those numbers. So I'm going to cross out the ones that are in the list. So that's 1, 4, and 7. So then the least remaining one is 2. So that's our K. And then I'm going to add the edge K A1 to the edges. So that's 2 to 7. And I'm going to mark K. So just put an X over it to show that it's marked. Okay. Let's pause here. Is this making sense so far? Yeah.
So it's K is the least of the unmarked vertices that is not in AI up to
Yeah.
Okay.
Yeah, so let me say and not. Okay, so now we've done 7. Okay, this is the key. 7 is still in this list, so it's still not allowed to be chosen next. Okay, so the next least one is 3, and we're going to connect that to the next number in this sequence, which is 4. And then we mark it. Okay. Now, the next least one is 5, and it's connected to 4. And I mark 5. Okay, now I think this is like one of the errors that I made when I was first doing this. So now the only ones remaining in the list are 1, 7, and 1. So 4 is actually allowed to be chosen now. So at this moment, 4 is like freed up, and also it happens to be the least one. So now I'm going to connect 4 to 1 and mark 4. Okay, is this like making sense and also seeming like I'm doing it right? Okay, so now the least one is 6, and it gets connected to 7. And we mark 6, and now 7 is freed up. So, and 7 is the least one, and it gets connected to 1. Okay, so now we've run out our list, and 2 unmarked vertices remain, right? Because we haven't marked 1 and we haven't marked 8, and we join those to make the final edge. Okay, and I'm gonna redraw the original tree so we can check if we got the right thing. Okay, so 3 and 5 are connected to 4, and then we're connected to 1, which is connected to 8 and 7, which is connected to 2 and 6. Okay, good. So we got the right tree back. Okay, so that's how reversing this process goes. And I'll give you a few minutes to reverse this one. So I'm gonna copy this code. So I'll give you a few minutes to practice by just reversing that one. So produce the tree using the algorithm. Okay, did it work? Good. Okay. So let me address one concern that you might have, which is like, why does this process give me a tree? Like it seems like maybe it's possible that as we're adding in edges, we produce a cycle or something. So why do we get a tree? So at every step, every component of the graph has only one unmarked vertex. So every component has exactly one unmarked vertex. So we start with n components, each of them is unmarked. And then as you go on, so that's true, this statement is true initially, and then every time you add an edge, it's between two unmarked vertices, and it leaves behind one unmarked vertex. So this is true initially, and each step adds an edge between unmarked vertices and it only leaves one of them marked. Unmarked. Right, so, so what's happening at each step? I have two components, each with an unmarked vertex. I add an edge between them, and then I'm only going to leave one of those vertices unmarked. So that has merged two components into one component, and that one component still only has one unmarked vertex. And adding an edge between two components, two distinct components, will not create a cycle, right? So I'm not creating any cycles. And after n minus 2 steps, we have two unmarked vertices and therefore two components. And then when we add the last edge, adding in that last edge is going to give me, it's going to merge the two components. So I'm going to get a connected graph out of it, and it has n minus 1 edges. So this leaves us with a connected graph with n minus 1 edges. And so then by the theorem from the recorded lecture, that means that this is a tree. Okay, does that make sense? Are there questions? Okay, so now what's left to prove in order to show that this process gives a bijection from trees to proofer codes is that we need to show that if I start with a tree and write down its proofer code and reverse the process. No, sorry, what are we gonna? Okay, so here's what we're gonna do. We're gonna start with a proofer code, produce the tree, and then show that the proofer code of that tree is equal to the original proofer code. And that's kind of what's left to do to show that this is a bijection. So what's left? What's left to prove? Okay, so we know that if we start with a proofer code, A1 up to AN minus 2, that gives me a tree T. So now we need to show, and we also know that T, there's some proofer code called F of T. So we need to show that F of T is equal to A1 up to AN minus 2. Okay, so here's the theorem. And this is just called Cayley's formula. And this was proved in 1889. And it says that there are n to the n minus 2 trees with vertex set S equals 1 up to n. Okay, so we're gonna, here's the proof. So, okay, so if n is 1, this holds. Because 1 to the -1 is 1, and we saw before that we had one tree. So we're gonna assume that n is greater than 2, greater than or equal to 2. And what we need to do is show that we have a bijection from trees. This is like the overall strategy. Just to recap, so we have a bijection from trees on S to the proof or codes. And to do this, we must show that for every proof or code, which I'll call A, there is exactly one tree on the vertex set S whose proof or code is this one. Okay, do you all agree that this is enough to show that this is a bijection? So it's surjective because there is a tree, and it's injective because this is like saying the inverse map is injective. I have to think about why this is enough to show that it's a bijection. Does anyone have a quick answer to why this is, yeah?
Prove that it's just like exactly. Cause you have like all the different proof of codes you can make.
I think that what this shows is that the map, okay, so here's what I'll say. So we have, yeah, okay. So we're gonna show that this map is a bijection. So start with a tree, produce a proof or code. So that means for every proof or code, there is a tree. So that means that this is surjective, and it's injective because there's only one tree that does it. Yeah. Okay, I'm good. Is everyone on board? Okay, so this is what we're gonna argue. And we're gonna do this by induction on n. So we're gonna go by induction. And we're gonna start with the n equals 2 base case. Okay, so there's only one tree with two vertices, and the proof or code is a list of length 0, and that's the only such list. So, so the set of trees that we're looking at is just this, and the set of proof or codes in this case is just the set containing the empty list. And it's clear that this is a bijection. Okay, so now let's go to the induction step. So let's assume that n is greater than 2. So given an given a proof or code, we're going to seek all solutions to f of t equals that a. So given a proof or code, we're going to seek all solutions to f of t equal a. So we want to find all the trees that achieve this. So I'm going to let t.
In the base case, isn't that not a tree?
Oh yeah, sorry, I should have an edge. Thank you. Other questions? Okay, so I'm gonna let T be such a tree. So the vertices appearing in the list f of t, which is equal to a, these are the non-leaf vertices of t. Okay, so why is that? Why are the elements of the list the non-leaves? I think it will be all of the non-leaves, right?
Even those like last two.
Oh yeah, maybe yeah, it's not gonna be all, you're right, it's not all of the non-leaves, but the ones in the list are not leaves. So why is that? Yeah,
They all connect to one other, vertex, that if you get rid of one thing, you can connect to another one. Doesn't make sense. So I just wish this.
yeah, exactly. So, yeah, like let's think about this. How does the algorithm work? We're gonna run through the leaves of the tree from least to largest and write down who is it connected to. So I'm never writing down a leaf. Yeah, okay, so the vertices appearing in that list are non-leaves. And maybe, yeah, okay, so they're non-leaves. And the first leaf deleted, so this is a claim. So the first leaf deleted is the least element of S, which is not contained in f of t.
Is S here?
S is the set 1 up to n. Yeah. So why is that? Yeah,
Because in the algorithm, we only delete it once, but we see of the whole graph. And then we add the ones that I think we saw in the connection.
yeah. Yeah, okay, are we in agreement? So let's call this X. And then the neighbor of X is the first element of f of t. Um, which is equal to A. So this is A1. Okay, so to recap, every tree satisfying f of t equals A has X as its least leaf, and it contains the edge xa1. Okay, so deleting X, maybe I should write that. So every tree satisfying f of t is equal to A has X as its least leaf. And the edge xa1. So now what we're going to do to make the induction go is I'm going to delete the leaf X, and that leaves us with a smaller tree. So I'm going to delete X, leaving a tree on vertex set, which is called, I'll just call this S prime, which is S, and we'll take out the element X. And this tree has proof or code A2 up to AN minus 2. I'll call that A prime. So we just lost the first entry of this list. Okay, are there questions? Okay, so now we're going to apply the induction hypothesis. So by the inductive hypothesis, there is a unique tree T prime having vertex set S prime and proof or code A prime. So f of T prime, oops, equal to A prime. And now, since every tree with proof or code A is formed by adding that edge xa1 to such a T prime, there's at most one solution to f of T equals A. So since every tree with f of T equals A is formed by adding xa1 to such a T prime, there is at most one solution to f of t equals a. And furthermore, this exists because if we take t prime and we add that edge xa1, this does create a tree with vertex set S and proof for code A. So we've showed that up to now, we've showed that there's at most one, and it does actually exist. So furthermore, this tree exists just by adding that edge xa1 to t prime. And that's the proof. Okay, are there questions? I feel like this is a lot to digest, like the proof for codes, the algorithms in both directions, and then also proving that that this is a bijection. So if you have questions, feel free to ask them. And also just like as you digest this, there more questions may come up. So feel free to email or write in EdSTEM. Okay, so that's Cayley's theorem. So now I'm going to switch gears a little bit and move towards the matrix tree theorem. And we'll see how this is related. So we can interpret this result in a different way. It counts the number of spanning trees of the graph Kn. So Cayley's theorem so we framed it as counting trees on the numbers 1 up to n, but it also counts spanning trees in the complete graph Kn. So just to kind of remind you of some things. So the complete graph on n vertices just has all possible edges. And then a spanning tree is a subgraph of this, which is a tree and hits every vertex. So for example, this would be a spanning tree. So we can think of Cayley's theorem as counting the number of spanning trees inside of this graph. And now we're going to consider the more general problem of counting the number of spanning trees in any graph G. So we'll give a formula for the number of spanning trees, and then Cayley's theorem will be easy to recover just as a corollary of that theorem applied to the complete graph. Does that make sense? So let's do an example. So I'm going to have you count the spanning trees in this graph. It's like the complete graph minus one edge. I'll give you a few minutes to do this. Do y'all have a number yet? How many? Yeah. Yeah, so, okay, yeah, so I'm gonna show you, so like, okay, where are we going? So, from now until like the end of today and maybe spilling into the beginning of next class, I'm gonna talk about, deletion and contraction, which gives kind of a recursive way to count trees, and then we'll go full on into matrix tree. So this like deletion contraction stuff is kind of like, it comes up pretty often when trying to solve problems related to graphs, because it turns out that a lot of times you can relate, so in this case, the number of spanning trees in the graph to the number of spanning trees in smaller graphs. And this is like a technique that comes up over and over again. So we're gonna talk about that strategy now and then matrix tree next time. So here's how it works. We're gonna count these by first considering the spanning trees that do not go through this diagonal edge. So you can pick any edge for this, but we'll just count the ones that don't go through that edge. And then we'll count the ones that do go through that edge. So for the ones that don't go through that edge, there's going to be 4 spanning trees corresponding to just deleting any choice of other edge, right? So we get that one, that one, that one, and that one. And then for the ones that do go through here, I can pick either of those 2 edges, and I can also pick either of these 2 edges. So I get one that looks like that, one that looks like that, one that looks like that, and one that looks, wait, I need the other, like that. Okay, and that should be all of them. So these are like not containing the diagonal and containing. So the observation here is like 2 parts. So the spanning trees of G that do not contain, let's call this edge E. Spanning trees of G not containing the edge E are spanning trees of what graph? Yeah, so this is going to be G minus E. Right, so if I want to know like what are the spanning trees of this thing that do not contain this edge, I just need to pretend that edge doesn't exist and find a spanning tree. Okay, but what about the spanning trees that do contain that edge? So I think right now we don't have a way to say what graph that should be related to. So spanning trees of G containing the edge E are spanning trees of what's called the contraction. So the book denotes this G dot E. A lot of times I see this written, so I think the more common notation is to write G slash E. But then that gets confusing sometimes because sometimes people write the deletion as G backslash E. And so it's like you can get mixed up pretty easily. But so it's just a side note on notation. So what is the contraction? So if I want to contract an edge, I basically just think of shrinking this edge down to a point. So all I'm going to do is take it out and then merge the two vertices that it was connected to. So the contraction G dot E. I don't know why, but I was again thinking that this class ended right now. We have 10 more minutes. I don't know why I keep thinking that it's over at 11:40. Okay, so the contraction G dot E is going to be the graph so this is the graph where, so let's say E, this edge, is equal to UV. So those are its endpoints. So I'm gonna replace U and V with a single vertex whose incident edges are the ones besides E that were incident to either vertex in the original graph.
You keep the graph simple, like merge two edges if one would be U and one would be V.
No, you keep them separate, yeah. Yeah, and you can get loops as well from doing this. Okay, with whose incident edges are those incident to either U or V in G, but not, and yeah, we'll exclude E.
Wait, so then how do you get on if you're excluding V?
I guess if you already had multiple edges between. So like, yes, so as an example, so like, let's say we had these two and we contract along E, that's gonna give me a loop. And in the example that we had before, so we had this, and we contract E and we get that graph. Okay, does that make sense? Other questions? Okay, so this gives us a way to count spanning trees. So I'll make a proposition. So I'm gonna let tau of G denote the number of spanning trees of a graph. And let's let E be a non-loop edge. Then we have the following formula. And this is exactly just as was in the example. So we're going to have that the number of spanning trees of G is equal to the number of spanning trees of G minus E and plus the number of spanning trees of G contract E. Okay, are there questions about the statement? So here's how the proof is going to go. So we're going to break this down into spanning trees that do not contain the edge E and spanning trees that do contain the edge E. And The spanning trees that do not contain the edge E, we've already observed that those are counted by this. So, the spanning trees of G that do not contain E are counted by tau G minus E. So now we need to show that the number of spanning trees that do contain that edge E is counted by tau G contract E. We need to show tau G contract E counts spanning trees of G containing E. So I'm gonna basically show this by making a bijection between these two sets of trees, because this is just, the spanning trees of this graph, G contract E, and I want to compare that to the spanning trees of G that contain the edge E. Okay, so if I have a spanning tree that contains the edge E, and I contract the edge E in that tree, that will give me a spanning tree of G dot E. So I'll write that down. So if we contract E in a spanning tree of G containing E, we obtain a spanning tree of G contract E. Okay, so why is that? Maybe let's justify that statement. So why do I get a tree out of that, and why is it spanning? Yeah,
Well, it remains connected and you're removing one edge.
yeah, so, okay, yeah, so it's gonna be connected and it has the right number of edges, so that means it's a tree, yeah. And then,
It's spanning because like the original tree spanned the original graph and the only like edge we're moving is between two vertices that are now one vertex. So we have like every vertex in the new graph will show.
yeah, exactly. Yeah, so maybe I'll write something, so it's spanning because exactly as you said, like it was originally spanning and all we did was glue two vertices together that are also glued in G contract E. Yeah.
What was the justification again for why it's still acyclic?
Yeah, okay, yeah. So I'll say we're good on spanning. And then why is it a tree? So it's still connected. So we're connected. And it has the right number of edges because it originally had number of edges in G, or sorry, number of vertices. It was originally a tree, so it had the right number of edges. We lost one edge, but we also lost one vertex. So we still have the right number of edges. And being connected and having the right number of edges is enough to show that it's a tree. Yeah. Okay, are we convinced? Okay, let's also observe that, if I have distinct spanning trees of G, I'm not gonna get the same spanning tree of G contract E by doing this. Do you all agree? So, no two spanning trees of G are mapped to the same tree of G dot E by doing this. Okay, and then the last claim is that every spanning tree of G dot E arises in this way. Oops, that's not the right G. And basically how you can think of this is if you take a spanning tree of G contract E, you can just expand an edge where that vertex is, and that will give you a spanning tree of G dot E. Or sorry, not G dot E, of just G that goes through that edge E. Does that make sense? So like, maybe I'll draw our picture. So in our example graph, this was the edge that had gotten contracted kind of in the growing out that way direction. So if I have a spanning tree of this, then I can get a spanning tree of the one where I'm not, where that edge has not been contracted by just expanding out that edge again. Does that make sense? Okay, so that finishes that proof. So we do not have class on Tuesday because there just aren't classes on Tuesday for some reason. So I'll see you again next Thursday. Hey.